Hello, this is the meeting of the Healthy Planet Action Coalition with Gene Fry, and I'll turn directly over to Gene to introduce himself and tell you about his talk. Gene.
Well, I grew up in Fayetteville, Arkansas, got a PhD from Cornell University in resource economics. I've lived in Massachusetts most of my professional career and retired, so I get to work full time for no pay doing what is my vocation. Um, I think my wife and brother have joined me. My brother lives south of Brisbane, Australia, and I've been studying climate change in some sense for 36 years, mostly on the side, getting paid for something else. Been able to pay more attention to it since I've been retired. Um, Had my Damascus moment 36 years ago. I heard a talk by David Ryan on a paper that he and Jim Hansen, Cynthia Rosenzweig did that modeled the future when we had doubled CO2, 4.3 to 4.5 degrees Celsius warming, and a once a century drought covering 45% of the earth and bad things to the food supply, et cetera. So I've got pretty interested since then. Um, so albedo feedbacks dominate current and future warming to 5 degrees Celsius or more. There. So this is the NASA temperature record since the 1880 when it starts. 5-year moving averages land in red, sea surface at blue, and both combined in green. Over the first 95 years of the record until about 1975, there was virtually no change in the sea surface temperature on net. It had its ups and downs. There was some increase in the land surface temperatures from the throes of Krakatoa, increasing from there. You may notice some ups and downs that are related to eruptions of volcanoes. We'll look at those later. The rate of change increased in 1975 to 2000, up to zero point 0.3 per decade for land, 0.15 for sea, and 0.19 for combined. The next and most recent quarter century, it went up again. At this rate, 2025, I expect 2 degrees to be breached soon after 2040, give or take a few years. And if this rate continues and does not accelerate further, somewhat more than 3.5 by 2100 if we do not do the things we need to do to keep it down. So Earth's energy imbalance, what comes in from the sun less what goes out from the Earth, has been increasing. The top graph in black shows a blue line energy absorbed by the oceans, which absorb about 90% of the incipient sunlight measured by Argo floats. The orange line is by satellite atop the atmosphere. The trend over this about 18, 17-year period is uh, a dotted line, and it corresponds to 17 to 35 times human energy use. The imbalance has increased since 2019. You have the green line in the bottom graph and the red one. The red one, which is the most recent here, corresponds to 45 times human energy use. And it seems, from what I can gather, that the imbalance is continuing to rise, although I'm not an expert on that. Go back now in time to the last 4 ice ages, an ice core taken from Vostok, uh, a station near the South Pole. Many of you have seen this. At the top, CO2, the middle, methane, and the bottom, temperature. I did not do sea level, which also all those tend to move together pretty well, but not exactly. So on the next slide, I'm going to get rid of the temperature horizontal axis, put the CO2 on the horizontal axis, and temperature on the vertical axis. Sample every 10,000 years is blue dots. And there we have it. The left vertical axis is the temperature, Vostok. On the right, I tried to translate the polar temperature to global based on the work of Carolyn Snyder in 2016, sediment cores around the world in the ocean. Um, the best fit line for CO2 alone is in purple. along with its equation, and for including methane as well, is in green. I did find at that point in my life 10 years ago a couple of um, data points that were back before the ice ages when it was warmer than today. And I was really surprised to see they fit the trend lines pretty well from when it was much colder than today. The extrapolating, we have 5.4 estimated equilibrium temperature for CO2 alone and 8.7 when you include methane, which is much more short-lived and I don't pay as much attention to. But why is there this big gap between the estimated equilibrium temperature? Why is it so much higher than today? And after a couple of weeks, it dawned on me it's because Earth will reflect sunlight, less sunlight, and I learned the word albedo. But I said, well, what happened when it was warmer than now? Can we not have to extrapolate and can do interpolate? And not many years ago, I found this pair of graphs, courtesy of a colleague at the University of Massachusetts. At the top is Earth's temperature, as best whoever measured it could do, over actually 500,000,000 years, and pretty similar on the bottom for CO2. One is log-log, one is log-linear. So what I did is match up the time roughly every million years from 7 million to 50 million years. From 1 to 6 million years, I was able to get it 2 or 4 times within a million years. And before that, I could get it more frequently from ice cores. So here's what I get for the past 20 million years. I would mention that temperatures farther back as well as CO2, but most interesting, temperatures get fuzzier. There are lots of effects which I'll just say make it fuzzier. And that's true for many different ways of measuring temperature as well as CO2. I was surprised to find that a little bit surprised anyway, to find that the R squared is very similar over such a long time period as it is over the Vostok ice cores, just 420,000 years. And the so-called predicted temperature is the same. I'm also aware that when we get to almost today's CO2 level, just off the right-hand axis, the six highest CO2 levels um, or the six most highest CO2 levels all have temperatures that are above the trend line. So I find that interesting.
Quick question, Gene.
Yeah,
Just on that one, you mentioned R squared, which is a fairly standard statistical measure. Do you mind just
yes.
explaining for people who are not familiar with statistics what R squared means?
Well, perfect correlation is 1 or 100%. Uh, no correlation at all is 0. Actually, R squared is correlation squared, it's statistics speak, but the closer you get to 100%, the more precisely, um, I guess I would say, you know what's going on and can be confident. There are other kinds of non-statistical problems which maybe you don't know it quite as well as you thought. How's that?
Thank you.
On
So
that,
now we're
on
looking,
that, Gene, on that, could you relate that to number of sigma, a confidence in sigma? Is that easy?
well, I
You have,
think a T ratio of 2 generally um, is 2 standard errors,
okay,
and that's about 95% confidence, is it's called.
okay,
And Six Sigma is like 99.999% confidence. But that's ignoring the other errors that might be out there in complex systems.
okay,
They're
thanks.
they're better stated for lab work. So looking at the left, the table at 1 million year resolution, the most recent 25 million years on the left side and the 25 million years before that on the right side, I call your attention to 24 and 25 million years ago, since CO2 levels were a little bit higher than today's 427 parts per million, namely 437 and 450. Temperatures then were 5.92 and 5.40 degrees Celsius. Observations between 450 and 710 parts per million CO2 are incredibly scarce. Only 2 out of the 50 are in that range. Up until 39 million years ago, look at the bottom right. Temperatures range from 8.7 to 13.2 degrees Celsius, much higher than most anybody is talking about these days, although maybe not everybody. Interesting question, which is answered by this data, is 350 parts per million, I think first suggested by Jim Hansen maybe 15 years ago. Is that safe? We have an organization called 350. So I looked at what happened when CO2 levels were close to 350, and that led me to 4 to 11 million years ago on the left side toward the top. CO2 levels were pretty consistent then from 336 to 368 parts per million, and they averaged 350, and the global temperature average is 3.2. So I answer that question, 350 is not safe. A safe level is going to be considerably less than 350. Quick diagram of the albedo effect. Again, albedo is how much light is reflected from the surface. In this case, the sunlight from Earth's surface. Snow and ice reflect most of the sunlight, not sure often as high as 90%. Whereas water, when the sun is at least somewhat overhead, absorbs 94%. It actually depends a bit on the refraction angle for actually both snow and water. Light surfaces reflect sunlight. They don't let Earth warm up as much. Changing the light surface to a dark one warms Earth, and we talk about the darkening of Earth in recent years. Changing a dark surface to a lighter one, what many people here are interested in, cools Earth. So this I came across just over a year ago in press conference for Jim Hansen from his later paper, Global Warming is Accelerated, etc. I've seen it other sources since then in different scales. The amount of sunlight Earth reflects dropped from the beginning of the record to from 29.36%, as I read it, to 28.72, and that's 24 and a half years roughly. That's a 0.64%. That may not seem like much, but we get a lot of sunshine, and it amounts to 2.19 watts per square meter of radiative forcing, which eventually leads to warming. You divide it by the temperature, and you have the rate, which is 3.5 watts per square meter per degree Celsius. So let's see what's happening with greenhouse gases over the same time period. This data is from NOAA, National Oceanic and Atmospheric Administration, end of 2024. And greenhouse gas is the big purple, CO2 greenhouse gas is the big purple at the bottom, and various other greenhouse gases above that. So from the vertical line at 2000 to the edge of the right, you'll see a dotted or dashed horizontal line for CO2. You can see how much it increased on the left and the right scale, which works out to about 0.73 watts per square meter. The other greenhouse gases stacked on top of it that do the same thing. You get 0.14, which add up to 0.87. Now, the previous graph on the previous slide went to 2025, so I want to extrapolate by multiplying that, add by 2/23 of that, it comes to 0.95 watts per square meter. The albedo loss from that previous slide was 2.19, and that's a lot more than 0.95. It's more than twice as much, and out of the total, which I would take by adding the two, albedo loss accounted for 70% of the radiative forcing. And that's roughly as much as accounted for by our greenhouse emissions to 1987. So the way I put it is warming from greenhouse gases is the trigger. Albedo feedbacks are the main event they trigger. The albedo feedbacks are self-reinforcing, amplifying feedback loop. Warming drives albedo loss, which drives more warming, which drives more albedo loss, etc. As I see it, albedo loss is unlikely to stop till long after humans stop putting carbon in the air. Oh, misspelled in. 9 to 10 years ago, I was looking at quantifying this, and I was able to find data that I could use on 5 albedo effects: clouds, sulfates, sea ice, snow, and land ice. I didn't do smaller sources, and I didn't find data for them. The most important seems to be clouds. This was the state of the art when I did my modeling, paper by Mark Zelinka and all in 2017, and found that the global average cloud albedo feedbacks were four components. Most of all, less percentage of cloud of Earth being covered by clouds as Earth warmed. That's in blue, called low amount. More high altitude warming clouds and fewer low altitude cooling clouds. Both of those are net effects. They do some of each. Um, is in red, and that's offset by clouds becoming more opaque. For seen from the ground, that might mean to say they're darker on average. The Zelinka's estimate of 0.47 was a little bit less than the midpoint of the range noted by IPCC in the most recent to him at that point assessment. The assessment is very wide, which means we didn't know at that point very well at all what the cloud feedback was, weren't even sure of its sign. I would note that this is about a seventh as much as the albedo feedback that's been measured over the last 25 years. The clouds do not account for all of that, but I think they probably account for the more than half of it, especially when you include their interaction with sulfate and other aerosols. Later in the same press conference, I came across this pair of graphs from George Seleutis at NASA and his colleagues. The color code, gray is the lowest percent of cloud cover, less than 45%. Black is 45 to 50. Dark blue is the next most. Regular blue, the next most. Light blue, the next most. The most is the dark brown, which you see toward the poles a bit, and red, which you also see near the poles in high latitudes, and orange also somewhat so. So I did some ancillary numbers. The width of the ocean at that latitude band of 10 degrees wide, for the Pacific is on the left side, and the Atlantic is on the right side. I would note that this extends 90 degrees, which is Arctic Ocean, and it also includes a lot of the Southern Ocean at the longitudes corresponding to the Pacific and Atlantic, is my take on that. In the center are the cosines, which basically near the equator, the sun is most directly overhead and produces the largest heating effect, and there putting a cloud in its way produces the greatest cooling effect. And those are used in weighting of the various observations, which come too soon. So this is the best behaved of the four ocean basins, North and South, Atlantic and Pacific. The closer to the equator, the thicker the line. So I have 9 different thicknesses there. The colors are arbitrary. You notice that closest to the equator, 0 to 10 degrees, which is black, has the lowest percent of cloud cover, 10 to 20. Next one is the next lowest. The third nearest the equator is the third lowest, and the fourth nearest the equator, especially after 1996, is the fourth lowest. And these really dominate the effect because that's where most of the ocean is, because that's where most of the area is. And also that's where the sun is most directly overhead. And I note that cloud cover in general decreased over all these years, and it was definitely lower, at least through up to 50 degrees latitude at the end of the period than it was at the start. However, that's the best behaved. There are others that behave fairly differently. It's not that different in the South Pacific Ocean, close to the equator, has the fewest clouds, but it's substantially different in the land hemisphere, the northern hemisphere. And it's strikingly not so in a clear way in the North Atlantic, where the second and third latitude bins close to the equator, had the fewest clouds. And there are substantially more clouds at the equator, and it's very clear, and not quite as many as 30 to 40 degrees north. In the Pacific, there's a big dip roughly after the eruption of Mount Pinatubo, but another one with a great El Nino after that. I don't know what all else was going on. Those jump out at me. The least cloud cover was the second closest to the equator. The next least was third closest. You actually have a lot of cloud cover in the Arctic Ocean, those thin lines, red and gray. And there's actually a good bit of cloud cover in the near the equator for the North Pacific. So the composite is here on the left. Um, let me try again. There we go. Um, and here we see that the least cloud cover was at 10 to 20 degrees north and south. The second least was closest to the equator. Third least was 20 to 30 degrees. I came across this diagram shortly after I did this composite and did all my work for each bin for each year, weighing how many of which color were in that 500 and some bins. And I noticed that at the equator, there's a lot of cool water in green spreading west from the west coast of South America and from Africa. Whereas at 10 to 20 degrees north, which is very roughly from Panama up through the north of the Yucatan or Cuba, there wasn't very much green at all, and it was especially intensely red, both off the eastern coast of Asia and the Asia islands, and also in the Gulf of Mexico and east, and to a lesser degree south in the Caribbean Sea. And at 20 to 30, you've got the intense heat in the Gulf of Mexico, but off the west coast of North America, you've got a lot of cold water. It's still pretty hot off the east coast of Asia. The Indian Ocean is irrelevant. They didn't look at that. So what I see is the warmest waters were 10 to 20 north, and it's not obvious whether the equator or 20 to 30 north would be warmest. And that's kind of what I see in the composite graph. I think of this as cloud cover with sparsest where, this is latitude, and when, it's mostly years, it was hottest. So putting that all together, using those bins and weighting them both by the width of the ocean at the latitude and by the cosine of latitude for the cloud's cooling effect, I come up with these for the Pacific and Atlantic Ocean. It's really very striking, to me anyway. And Pacific cloud cover fell from 62% to 55% over 33 years. Atlantic, 58% to 50% over 32 years. So that's a ninth of the initial value for Pacific and a seventh of the initial value for the Atlantic. I think of clouds as intercepting something like an eighth of the incoming sunlight, and the Pacific Atlantic Ocean, including what they counted here as the Southern and Northern Oceans and the Mediterranean Sea, as covering 55% of Earth's surface. So it's a really big deal. And I'm at an impasse or haven't had time to struggle with translating that to watts per square meter. So, so I was wondering what's going on, and has anybody had any theories? And I came across primarily this from published by Schneider and colleagues in 2019, two leading explanations. In the interest of keeping this shorter, I'm going to let you look at that on your own. And these are a couple of explanations. The third one is evaporating clouds, and I'm sure there are others, but these are the ones I came across, and I'm not at all qualified to say which is better, if any. So now switching gears a little bit, CO2 levels in Earth's atmosphere, they've gone up somewhat smoothly, except for the within the year sawtooth pattern, which I've not put on here. There seems to be an interruption, acceleration about 1950. And I'm not seeing much acceleration in percent terms after about 1995. It's an acceleration in parts per million terms, but not in terms of percent. So the question I ask is, why didn't global temperatures rise as smoothly as CO2 over the course of the temperature record? And this is a very live question 10 and 20 years ago. And I looked especially at 1940 to 1979, 1975, which when a lot of industrialization, there's a lot of CO2 going up in the air, which we saw in the previous graph. I also looked at, gosh, it goes way down sometimes. This is land surface temperatures, which are more variable than, and generally warm faster than sea surface. But this is where I had the data, and I thought sulfate in the troposphere, which originates on land, is probably much more found over the land than it is over the oceans, although not exclusively. And it dawned on me, sulfur emissions went up 110%. I was able to find some data for sulfate levels in the air, but very low time resolution, and sulfur SO2 emissions, which I found at much better time resolution. Kind of put them both together in various slides I'm not showing. What really strikes me is we've got 5 very major volcanic eruptions which cool the Earth off for some years afterwards. I think the 5-year running average unexaggerates the cooling at any particular year. We've got especially big cratering after Krakatoa in 1883. And anyway, I found data and I put together this equation using years that are not affected by volcanoes, which is a lot of years considering the 5-year average I use for the mean, and said temperature is a function of CO2, methane, and sulfates. The adjusted R square was almost 100%, very good. T ratios 6.4 to 8.7. You can be much more than 99% sure that there's an actual effect for all 3 of them. And I used the coefficient for sulfates later on in my predictions going forward. And maybe also in my analysis, actually also in my analysis of the past 40 years at that point. Turning next to sea ice, Arctic minimum sea ice, upper left. As the ice recedes, the darker ocean below absorbs more heat. The water will warm more, even without more CO2, as long as it keeps heating up. You're down about 40 to 50% from the beginning to the end. Volume is down 60 to 70% because the ice got thinner too. That affects sea level rise, but it does not affect temperature. The annual average on the left for Arctic sea ice area is down 15%, and on the right, Antarctic, which when I started this was on an upward trend, is now down 10%. Next up is snow. 2 studies, one by Chen, Northern Hemisphere snow found over 32 years, found 0.21 watts per square meter per degree Celsius, little less than half of what Zelenka found for clouds, and about 15% as much as we saw for all albedo effects from the graph I got from Hansen about a year ago. Then I did a little cross-section analysis 2018 across transects 14 US and Canadian cities, and I had data on how snow days change as we move toward the poles and also how temperature changes as we move toward the poles. Use that to estimate that northern snow cover decreased about 9% per 1 degree Celsius global warming. So it should be gone about 10 or 11 degrees. When Earth had 8 degrees more warm than now, we did not have ice in Antarctica, but it started forming at about that point. So it's not too far off. And maybe it's exactly right, even possibly. Land ice. Most of the land ice is in very thick Antarctica and Greenland, so the area decreases very slowly. Most of the sea level rise from ice right now is from Alaska, northern Canada, Russia, South America, and a little bit from the Himalayas. But land ice albedo loss is much slower. Those account for less than 1% of Earth's area. Antarctica and Greenland, multiple percent. So I put the albedo effects that I had data for and direct forcing and indirect forcing for from clouds and water vapor feedback. Water vapor feedback is known very exactly, and cloud feedback used to be totally wide open. I got that the sulfate loss, 0.185, was the biggest factor. Snow cover timing change, second. Arctic sea ice loss, third. And land ice loss, trivial, as was at that point, Antarctic southern sea ice loss. Added them up, divided by the total warming over the time period, got 39% of warming came from albedo changes. I took that to be as we put fewer greenhouse gases in the air, that warming in the future, especially beyond 2100, will be dominated by albedo changes and their feedback. And stuff I've learned since then confirms me in that belief. So what produces how much warming? I'd seen black box numbers from global climate models, but I couldn't partition them into what. So this is what I came up with. Earth will warm 2 to 4 times more, even if we stop emitting now. Almost 0.4 degrees Celsius for coal sulfur emissions, which are down now by about 30 to 40% from what they were at their peak. Still got phytoplankton and dimethyl sulfide, which is a non-human source of sulfur emissions. But anyway, northern sea ice and vanishing southern sea ice, about almost zero point 0.4, probably more like 0.35 now, similar for coal. And receding northern snow cover, the error bars are larger on that because of, don't know that well, the albedo underneath. Carbon sinks turning to carbon sources, that's very large error bars. We don't know very well the time frame under which that unfolds. It may be similar across oceans, permafrost, forests, and warmer soils. It may be somewhat different among them. And I'm sure there are different people who have different estimates to the extent that anyone does. Receding ice at the poles, maybe 0.2 degrees Celsius over the time frame. Some left after the end of our 2400 time frame. And the multipliers for water vapor and cloud cover, it's exact multiplier for water vapor within 0.001% or something like that, but still wide open at that point for clouds.
Can I just ask a question? My brain is a little bit addled by all this information, so I'm probably missing something really elementary here. But the pluses here, like you say, almost 4 degrees phasing out. So I take it
0.4, yeah.
that's 4 degree warming, but then okay, receding, vanishing. Okay, but then when you say receding snow cover and you would think that that would also cause warming, but it seems to be calling cooling. And
That's an
then,
approximate, not a negative sign. It's approximate.
oh, okay. I was like, what's going on?
Same thing for carbon
Okay,
sinks and
okay,
sources.
yeah. Okay, that would make sense. Yeah. So it's
And
all warming, basically.
yeah, it is.
Yeah. Okay,
And
thank
some
you.
of those are probably closer to 0.3. Carbon sinks turning to sources is uh, unknown, and that's very wide error bars.
Warming
But
by when?
2400.
Okay.
So I concocted 6 scenarios back in 2015. The worst one is 20-year delay in the peak emissions. The second worst one was an immediate peak, but not phasing out by 2050. That's in brown. Fossil fuel emissions phased out by 2050 is in orange. It's hidden up until 2050 under the green and blue, and it's hidden after 2050 under the magenta, which is when we stop emissions cold turkey, which isn't going to happen. The economy won't let it. And then 2 scenarios I had for CO2 removal. I would describe those now as removing about a quarter for the blue line and about a half of CO2 emissions to date. And to date was probably best described as a number of years ago. We may have a 2025 peak now. I mean, China's down 1.6%, I think, over 2024, and India was down 3%. US was up a little bit. But we're in the plateau area where our emissions are peaking. So how does that translate to CO2 levels? And here, I thought that carbon sinks turning into sources as the surface and other parts of the earth warm up would be very important. And I made some educated guesses. Those educated guesses are very important for estimates of future CO2 levels, and also they play in very strongly into future temperature. And these developed, my model had a decadal resolution, and it's tuned in to the, at that point, recent past and the recent present, which is about 10 years ago. And my judgment, based on projections I got from somebody else on permafrost, evolving, thawing, and giving off CO2 and CH4, I did a simple multiplier of that for oceans, warmer soils, and forests, and God knows if I got anywhere close to right by doing that. But I got that the CO2 emissions at the end of the period, anyway, were about half as much from the carbon sinks turning to sources as they were from the input by humans of putting CO2 in the air. So that's a really big deal. Before we go to the next graph, I'm going to turn to what 4-degree warming looks like. And that's where I came in 36 years ago. And it's slightly drawn from that, but mostly it's drawn from the report by the commission led by Stern to the governments of the United States and Britain. And highlights are freshwater shortages afflict almost everyone. Crop yields fall in all regions. It got 30 to 50% in the US, but that was 4.3 and 4.5, not just 4. Entire regions cease agriculture altogether. Great migrations and water wars become intense. 2/3 of Amazon rainforest will likely turn to savanna. It should be similar in the Congo. Both of those have become sources more often than sinks these days. Methane release from permafrost accelerates more, no surprise. Atlantic circulation slows by half. I didn't much know what that means at the time, but there's a lot of people talking about that these days. Ice sheet collapse speeds up in West Antarctica and Greenland, and gradually more and more blocks and areas of cities sink beneath the waves, and some of them are pretty much beneath the waves. Amsterdam and Venice come to mind. 20 to 60% of species face extinction. Mammal rates of extinction are already hundreds of times background, and this was 10 years ago. At times, many places around the world, including U.S. Southeast, it's too hot and humid to survive outside long, becoming uninhabitable. So here's the forecast or predicted temperatures given the input assumptions that I came up with. Paris target, blue dashed line at 2 degrees. Kansas gets hot as Las Vegas, where you can't grow food in much of the United States, is the brown dotted line. And you have your 6 scenarios. I would notice that the successful emission reduction approach is in orange, and it crosses 5 degrees about 40 or so years later than the worst case where we peak in 2035. So that 5 degrees is the line where I feel saying that's where civilization collapses due to dearth of food and fresh water. Food supplies, I expect, are down by maybe 2/3. Fresh water, perhaps more, plus large areas like 10, 20, 30, 40, 50% of the currently inhabitable area becomes uninhabitable. So that's the bad news. And the news is we can do something about it, and that's what people in this group are dedicated to. Anyway, we must prevent this from happening. Two major school thought. One is taking carbon out of the air, get it back down to safe levels. 8 major methods on the left. They each have their pros and cons. Since we have a few guests, I'll say a little more about them would for than I would just for this group. Direct air capture is the easiest measure and it's permanent, but it's high cost. People are trying to get its cost down by using something other than heat, which is high energy cost and high cost to separate the CO2 that's been captured from its substrate or catalyst. And there are methods being explored like different electric charges, different relative humidities, or a couple others I don't remember. Uh, Probably my next favorite are enhanced rock weathering and its ocean cousin, ocean alkalinization. You grind up rock finely. A lot of that's already done at many different mines, tailings, and you spread them either on the soil or the earth, or you spread them in the ocean. And they're hard to measure the effects, but they're not expensive. Biochar is great, but it's limited amount of biomass in land. Keeping expanding forests is wonderful, except forest burns, and they burn twice as much area to 7 times as much area per degree Celsius of warming. So it's a very tough situation. Organic farming and fast rotation management are cheap. The question is primarily about durability, and a secondary question, do they actually capture, puts carbon in the soil or just move it around? And then there's farming the oceans. I know one of our members is very much involved in that, Brian Hertzen, who I had the pleasure to meet once. The other way of doing it, the third leg of the stool, is cooling off Earth. Cooling buys time to stop CO2 emissions and remove all the CO2 we have emitted, the legacy CO2. It delays and slows carbon sinks, turning into carbon sources, and it saves billions of lives. Look at the next to rightmost column. I have circled in red global stratospheric aerosols, potentially 1.5 degrees Celsius of cooling by 2050. That's a little bit more than your biggest volcanic eruption, where we've observed the eruption carefully and its temperature effect carefully. Other significant cooling ones, which don't overlap that, down at the bottom section, are marine cloud brightening, reducing black carbon emissions, and putting sulfur back in the troposphere from ships, which they were until recently, till 2020. And those add up to maybe 0.6. We've not put in cirrus cloud thinning and white balls on the ocean, have put in mirrors. Anyway, together, those can probably give us...
Gene, can I just, one comment? You
Yeah.
probably, most of the actual quantitative estimates are from Mike, so at least you want to, it's Ron, Mike,
Oh,
and a
I
bunch
didn't
of
know
other
that.
people. So, yeah, yeah, thank you.
Okay. I had no idea where they came from. But anyway, those add up to 2.1. If you also do work on methane emissions, which is actually more like CO2 removal, except it's CH4 removal, you can emit less, which is kind of like stop putting CO2 in the air, stop putting methane in the air, and take it out, which is catalytic methane removal. This says up to, between the pair of them, up to 1 degree Celsius added to the 2.1 cooling. So it's conceivable with that if we work at it really hard and get all the buy-ins that we needed, that we could cool Earth up to 3 degrees Celsius by 2050. And we're probably going to be looking at 2.25, 2.5 degrees warming by then if we don't do this. One caveat I have is that for stratospheric aerosols, it's best to use ones that don't involve sulfur. That's much kinder to the ozone layer. And it's also saves about 20,000, hopefully, lives a year. It's not 2 million people a year dying of sulfates in the troposphere, but it is 20,000 from dying from sulfates from the stratosphere. You only need about 1% as much there. So,
Thank you for presenting, Gene Sandhaven. I have a quick question on the risk comparison between
okay.
between SRM, SAI, which is low, and marine cloud brightening, which is deemed to be moderate. So that's interesting to me. Could you elaborate?
Well, I don't think of marine cloud brightening as having much risk. I'm not very good at going backwards in this, but there are some people, many people, scientists are really scared of stratospheric aerosol injection. A year and a half ago, David Keith, who works on both CO2 removal and direct cooling, and a couple of colleagues did a paper which they looked at, well, what if you do it and what if you don't? And there was a widespread of estimates in both, so there's a fairly widespread difference in the answers, but the central estimate was that 14 times as many people die if you don't put up stratospheric aerosols uh, as if you do put up stratospheric aerosols. And it's not clear at all that more people will die when you put up stratosphere aerosols than people who don't die because you put up stratospheric aerosols. It's going to be negative effects in some areas, but positive effects in others. And it's not clear that the net of those is negative at all. I think David Keith would make that point. So anyway, just to summarize. Oh, go ahead.
Yeah, I think your numbers in
hang
methane,
on, Bruce.
kind of high, but that's okay.
Bruce, what we'll do is hopefully Gene's just got a couple more minutes, and then when the presentation finishes, we'll have moderated questions. So let's just leave the questions until Gene finishes, and then we'll come back for discussion. Thanks, Gene.
So I have this slide and one summary slide at the end calling for questions. So jointly, carbon dioxide and methane removal and direct cooling could hold warming well below 1 degree Celsius after we end CO2 emissions. And I think it's not impossible to do that before 2050, and I think it will be done before 2070, thanks to China making renewable energy dirt cheap and electric cars too. And that would forestall most carbon sinks turning into sources, save billions of lives, and preserve civilization. So just to reiterate, we need to do 3 things. 2 of them won't work. We need all 3 simultaneously. Stop putting carbon in the air as quickly as reasonably possible. Take carbon out of the air, what we've already added, legacy emissions, and any future emissions, sooner the better. And screen out enough sunshine to cool Earth until CO2 returns to about 300 parts per million. So why don't I end the show there and ready to take questions.
Great. Thank you very much, Gene. And that was really superb. And it just such interesting material. So we've got first questions from Bruce and Robert. Over to Bruce Parker.
Yeah, one quick thing on methane. My
Okay.
Looking there, we're currently at about radiative forcing overall is about 3, a little over that. That's aerosols is about add subtracts 1. So we're really at about, for all the greenhouse gases, we're really at about 4 watts per square meter. Methane is only 0.6, which is about 1/7 of that. So I don't see how, and we're only at like 1.5 degrees now. So how can reducing radiative forcing by 20% reduce the temperature even by a degree?
Well, methane effect is funny. My own research, both on the Vostok ice cores and also with sulfates data, suggests that methane has a much larger relative role. Early versions of what I did called Global Warming So What, and I've had hundreds of editions of that slideshow, which grew willy-nilly over the course of many years, say that after you subtract out the warming caused by water vapor, the carbon dioxide counts for about 55% of the remaining, and methane, both direct and indirect, for about 30%. And there are different things out there, but based on the equations I have both for the Vostok ice core And for the sulfate analysis, I'm not persuaded that methane is that small in its effect compared to CO2. It may be. There are other things out there, but those are my thoughts for what they're worth.
Yeah, I mean, if you look at IPCC stuff, the radiative forcing of CO2 is about 2.3. It's about 4 times that of methane.
Yeah, I think that
So just
diagram
this
I
question,
had from
I
NOAA
think we
is
need to go back.
consistent with that.
Yeah, I just think it needs to be. And again, by the time if you reduce all the methane, if emitting it all, there's nothing left to catalyze. It comes out of their air in 12 years. So you can do one or the other, but not both.
To some degree, you
Double
can do
counting, you can do
both, but
both.
they may be overlapping. I mean, there are natural sources of methane that we can't do anything about, and that probably amounts to about 700 parts per million out of our 1930 parts per
Yeah,
billion.
yeah. Anyway, food for thought.
Yeah, it
Thanks,
is.
Bruce. Robert, unmute, please.
Right. Okay. Can you hear me? Good. Yes. Great presentation. Very, very good. I thoroughly enjoyed that. Gene, I think in your penultimate slide, you made your summary was that there was 2.1 degrees of cooling.
Yeah.
Yeah. Now, I assume that is not net cooling. So we're not going down from 1.5 degrees above pre-industrial to 0.8 or whatever it is, 0.6 below industrial. So when you get your 2.1 degrees of cooling, where do you think the net anomaly will be?
I think it would be unwise to do 2.1 degree cooling while without it we're at 1.7. That would put us minus 0.4. It's possible. It may be that we could actually do that, but I think it's undesirable. And that depends on the accuracy of the 1.5, which I understand Mike McCracken had something to do with. And I don't know, maybe those things won't pan out to be as effective, and the best we can do is 1.5 among stratospheric aerosols and marine cloud brightening, cirrus cloud thinning, and all the other cooling techniques, white minispheres on water, etc.
So is it your kind of policy view that we should be aiming for 300 parts per million, which is about 1 degree?
I think that would be a good policy. Possibly as low as 280, but I think 300 is a good round number. I think 3.5 is too much.
And that corresponds to about 1 degree of warming.
Somewhere around there, yeah, approximately 1 degree.
So the amount of cooling we would need to do, or reduced warming, would be dependent upon of that 2.1. We'd only have to do enough of it to get back to 1 degree of warming.
That is my opinion. My guess is it's probably possible to do enough of it, but I don't know that. I'm much less knowledgeable than other people who would probably also say they don't know.
Okay, great. Okay,
For what that's worth.
It was a great presentation, but I think it kind of fits rather neatly into that very short message I sent out earlier today about the fact that we use the word cooling in a somewhat misleading fashion, because we're actually not talking about cooling here. We're talking about less warming, and we need to kind of understand that.
A different way of saying the same thing, in my opinion.
Well, they're not quite the same thing. They're not quite the same thing. Less warming is warming.
Okay.
Thanks very much, Robert. So I really appreciated your presentation, Gene, and I'm giving a talk to MIA, the Mirrors for Enhanced Earth's Reflectivity, next Sunday afternoon, and I've shared the link to that on the HPAC email list, and I encourage people to come along to that. And what it raises for me is what can we do about it? And given that we've got this polarization between people who say just carbon action is sufficient and the denial community, which is essentially the fossil economy. There's a need for a third way in climate policy, and so your assessment that albedo is the main event is a really crucial insight into climate politics and policy, and so the need to get people to recognise that albedo is the main event. It raises this very provocative idea that action on carbon is actually quite marginal to short-term temperature. Like, it's obviously essential to long-term temperature stability, but in terms of the short-term impact, nothing we do about carbon makes a difference if we do nothing about albedo. And I think your explanation of the cloud problem is really very crucial, because Hansen estimated that cloud loss is 62% of the albedo loss, and so the albedo loss, the temperature rise from albedo loss, from the feedback, is just swamping any temperature effect from the carbon addition of new greenhouse gases. And so I just wanted to make those comments to welcome your argument. And my view is that what's needed is an albedo accord to focus governance attention on albedo, and using the Montreal Protocol as a model is really valuable, because especially because of the alliance between business, science and government. At the moment, we've got a real split between science and business over carbon policy, but there's the potential for science and business to ally to restore planetary albedo. And so that's where I see the Montreal Protocol, which has protected the ozone layer, and we can think of the albedo layer as analogous to the ozone layer. So clouds, ice, snow, and aerosols.
Just some thoughts on what you've said. One, I appreciate all the work you're doing to get some regulation and to get some agreement. I think actually CO2 removal and albedo increase, rebrightening the earth, will not face as much resistance as stop putting carbon in the air. You have tremendous money invested in putting more carbon in the air, the oil, and to some degree the coal lobby. We've had limited success with pricing carbon. There's pretty good success in Europe with it, and there's somewhat good success in China, although China's gone the complementary route. Instead of increasing the price of carbon, decreasing the price of non-carbon, and they've done a wonderful job of that. I think what I want to do is get out in the eyes of the public that if we do nothing, we're fucked. And we need to take action, and we need to do all three. It's not a matter of doing one first and then the other. We get a lot of bang for the buck from albedo change. CO2 removal is a much slower process, and we're going to get very uncomfortably high temperatures if we discard albedo work and just focus on CO2 removal. It's not enough. And God knows only stopping putting carbon in the air is way not enough. So those are some reactions I had to some of the things you said. I didn't remember all of them, but I hope that's perspective is a little bit helpful.
Thank you, Gene. So back to Ron.
Thank you, Gene. That was a really excellent presentation. Although it's quite dense with all the graphs and the figures and so forth. You will share the PowerPoint, I hope. Yeah, because I just had three comments. One is quite obvious because I see there's a number of people here who are not the usual folks, and so I do want to encourage you to take a look at our open letter. I put the link in the chat, and we need 12 more signatures. So I'm really and then we are going to submit it and hopefully publish it. So it includes the table that Gene put up in one of his slides that you saw there. Just another two quick points, and I see Mike is coming after me, so he will know a lot more about these things. But we put in the 1%, the 1 degree cooling. If you look at the tipping point literature, they refer to that 1 degree as really the edge of where the risk starts increasing for many of the major tipping points. So we were asked about that by the reviewer on our cooling paper. Sorry, that's my granddaughter. I'm in the hospital here. She just had a procedure.
So is that one,
so
is that
that is
1 degree?
that is actually a rationale. There's a lot of evidence from
Is that one,
references
Ron,
in the cooling paper. Sorry?
is that 1 degree above immediately in pre-industrial or 1 degree more than now?
No, 1 degree above pre-industrial. Yeah.
Okay.
We need to bring it in. And I think Mike, this goes back a number of years, but Mike actually sort of we were trying to figure out what should be our target. And I think that's where as I recall, Mike sort of proposed the 1 degree, and I don't know if he had all that evidence in mind, but we went back and looked at the literature, and indeed that is where the risk starts. Some of those tipping points is right at 1 degree. The other point
coral
is
reefs are already gone. Coral reefs are already beyond hope.
No, I think that the graph you put up about that stuff needs to get out there. That is just hair on fire, shocking stuff when you talk about the actual effects on species and humans and migration, and I mean that's what we need to get out to the politicians, to the decision makers. On methane, one other point is there does seem to be a close correlation between methane and water vapor. So it's the impact of methane is somewhat it depends. I think it's a big feedback related feedback, at least as I recall in our methane emissions, because we're saying we need to cut that as fast as possible.
They both necessarily increase with warming. And methane has a number of natural sources, whether it's wetlands, permafrost, even termite mounds that come to mind, and unfrozen soils where they're kind of wet will yield methane, and you warm things up and you get more of it. I think the relationship is not as exact as you have for water vapor from warming, but it's there.
Yeah. Okay. Thank you. Yep. Thank you. Excellent presentation. Thank you.
Thanks, Ron. We'll go on to
Mike. Thank you. So, Gene, that was it was interesting. So a number of us have said for quite some time that you don't actually need models to prove that this is an issue. And what you've done is basically go over a lot of the ways you can learn from history and from paleoclimate and other things to do it. And you get an answer similar on the sensitivity and the vulnerability of the Earth. So, there are those people who keep saying, "Oh, models are only theoretical, and it's all a result of theoretical stuff." And you've basically, I think, done well in doing something by sort of looking at the data and the observations in paleo to get it.
Thank you.
Which is interesting. I guess what I wanted to ask about was, do you think what you've done is really different than what models are doing? I mean, you don't, as near as I can tell, include the IR effect of clouds in there. I mean, and you don't seem to differentiate between types of clouds, namely convective clouds and cirrus clouds. As you go to greater temperatures, as you go from high latitudes to low latitudes, high latitudes tend to have a lot of stratus clouds because you don't have convection that can get going up there. But in low latitudes, you have sometimes more convective clouds, which are narrower and higher and have different effects and stuff. So, you were
That's
showing
not
low
part of my
latitude.
knowledge base. Yeah.
Yeah, I mean, you were showing low latitude cloud cover going down. Is that a result, for example, of stratus clouds becoming convective clouds? So yeah, you lose some reflectivity and you get a different effect and stuff. But I guess you don't have the infrared effects of things, and infrared matters a lot with cloud cover and stuff. So I guess I'm interesting. It comes out about the same effect, but
So you
uh,
retired from Cornell. Do you live near Ithaca?
mhm. I'm sorry,
Do
what?
you live near Ithaca? You retired
Uh,
from
no,
Cornell.
no, I live in Bethesda,
Oh, okay.
Maryland.
I you know
Well,
an awful
you can
lot that I
tell.
don't know, and I was hoping for some tutoring.
No, you can. I mean, when you go out at night, if there's cloud cover, it's not going to get so cold. If it's clear, you're going to get much colder, um, because you can radiate heat away pretty readily, and so IR effects matter. The average temperature that people use is the average of the minimum and the maximum. So I guess I just think it's interesting to be able to do that. So I don't know. I mean, it's interesting. I'll write some specific things, but I should also, on the questions and the discussions come up. So those were sort of estimates in that table of the maximum plausible effect we thought one could practically get by 2050. So not the ultimate effect over time. CDR effects were generally small because it takes a lot of time to build up the industry. We just didn't think that was going to happen. We didn't do the mirrors in space, although that may be the ultimate thing. If that group itself is quite interesting in what they're trying to do, and that may be something that takes over and sort of gets past some of the shortcomings of stratospheric aerosols over time, and everything. I mean, so you're starting out with what you can, and then you improve along the way and stuff. Um, I
So yeah,
guess.
indeed, there's a lot of gaps in my knowledge. I've never taken a meteorology course. I come at it from a different point of view, and there are a lot of subtleties I don't think I get, and not very much capable of putting them in. Um, I rely on other people's data, and maybe I could
I mean,
learn more
meteorology is
about
sort of
these
more about,
different kinds of clouds.
yeah, meteorology is sort of more about the variability in the weather and stuff a lot. And so it has different effects, which is interesting. I mean, you're coming at it from a thermodynamic view, which is the background I had when I did some of my early modeling and stuff. So it is kind of amazing that the Earth is so sensitive. We've had a Holocene that's been relatively stable for 10,000 years, 8,000 years, and you sort of think, how can it be changed? And then you look at paleo stuff and you see how much change can occur over Earth history. And
Somebody said
that
recently, I
really
don't
worries
know.
you.
Somebody
Uh,
said recently, I don't know if that was you or may have was Ron before you, but I suspect it was you. How does this compare with model results from global climate models? What I have uh, able find a little bit that says there's something called the uh, Global Intermodel Comparison Project, I think it is. And there
yeah,
seem to be two editions of that, round 5 and round 6. I think that round 6 may be more advanced in some ways since it's more recent. And what I notice is the estimates of climate sensitivity are increasing. Hansen is far from alone in saying that climate sensitivity is significantly more than 3 degrees, which comes out of, I think it's called the Charney Report back in the late 70s, which I don't know if you're involved with that at all, but um, I came across some source that compared about 34 models, both round 5 and round 6. And couple of them, well, the average was, I think, estimated climate sensitivity of round 5 was in the range of 3.5 as being a mean, and the round 6 was more like 4.3. There were 3 or 4, not Hansen at all, but others that were between 5.5 and 6 degrees. When I look at the past, I get numbers probably a little over the 6, but climate sensitivity, as far as I can figure out, is highly sensitive to the amount of ice left on Earth and probably changes according to that to some degree. So those are thoughts I have on climate sensitivity. And I remember when I first looked at the Vostok ice core data for 4 ice ages, came up with something around 8. I think as we have less ice, the climate sensitivity probably falls. But I'm not an expert, but I'm interested to see the trends in people who know an awful lot more than I do about climate modeling. So that's just a thought to something I think you said a little while back.
I would just say that global average temperature is just sort of a terrible metric. The land temperature change over land is about twice what it is over the ocean.
Yeah.
It depends a lot when you look at ice cores or what's happening, what you get and how you extrapolate that to the world, comparing over land and over ocean and what it should be to get to a global average. And it matters a lot depending on latitude, because at low latitudes, most of the trapped energy goes into evaporation. So that can raise humidity or transports heat out otherwheres and everything like that. So yeah, it's just that, yeah, I don't know. It's interesting. I will just conclude and say that by paleoclimatic approaches, by looking at that and analyzing it, you can show this is a serious problem. You don't have to have models. It's hard to say if you're completely specific, be precise on some of the things and everything. Hansen high sensitivity comes in part from considering some of the longer time scale feedbacks that people don't have in their models and stuff. So, I think he would say that you have to allow for change in land cover change or something like that, and vegetation change, and go through that and what systems there are. And there's, he's probably including permafrost and carbon cycle and other things and getting a high number. And some of the GCMs have some of that, and some of them don't.
Yeah, I think some of that is implicit in my approach.
We all agree with your conclusion. You got to do all three. So
yeah.
All right, thanks, Mike. And we've had questions in the chat from Sander Apima and Sev Clark. Sander, you're welcome to ask your question if you'd like now.
Thank you so much for your presentation, clear presentation, and all your comments. I'm just wondering about the potential research that has been done in climate modeling for SAI versus MCB, marine cloud brightening, as that supposedly is a more localized type of effect that you would be able to test in field trials as opposed to SAI. So I'm wondering about that. Thank you.
I'm not sure that I can tell you very much that you don't already know. I don't really know about the field trials. There have been various perspectives on marine cloud brightening. I don't think you're worried about people breathing it in, and your effects are much more local. You can turn it on and off just like that. Whereas stratospheric aerosols, you inject them and they take, a median time perhaps of somewhat more than a year to fall out of the stratosphere. But I'm not one to be able to answer your questions very well.
Sure.
Okay. All right. Well, thank you, Sander. And Sev, we've got just over 10 minutes left, and we've got Robert and Bruce with their hands up, but I'll just check with Sev if you wanted to ask a question. Unmute, please. Hang on, Sev, you're muted.
Gene, some of the early graphs you showed where there was curve fitting, it seemed as though a straight line graph was a better curve fit than the declining ones which you put in. Can you explain how you got that curve fitting, what curves you fitted to it?
Well, I started out many years ago thinking about greenhouse gases. They become more concentrated, and something that's absorbed and re-emitted toward the Earth's surface at 5,000 feet. As you get more of them, there may be ones in front of that, 3,000 feet. I'm sure there's a more scientific way of saying that, but that's how I think of it. And I've seen that same shape with respect to air pollution, particulate matter, which led later on to a focus on PM 2.5. A lot more doesn't produce proportionally more effect. I've seen that in particulate air pollution. It made sense for greenhouse gases. But I thought, I don't know that that's the best approach for albedo changes. So I tried getting a linear rather than a logarithmic fit. And indeed, it does produce higher estimates. But I carried that out to truly much higher CO2 levels. And what I got was effects that were higher than what's been observed over the last 50 million years, especially 25 to 50 million years ago when we had, temperatures 13 degrees, 12, even almost 14. And I thought, well, maybe there's some reason that albedo effects have that same kind of decreasing effect with more input. Maybe it's that you just get rid of the clouds at 11, 12, 13, 14 degrees. Albedo is driven partly by ice and its cousins, mostly snow, and it's driven by aerosols, which are generally pretty modest in the back through the most recent ice ages, as far as I can tell. Well, they're more modest compared to now. They were probably a little bit more so than during warm ages before that. So it's a slightly better R squared, slightly better fit to the data, but when you take it out to the end result of high levels of CO2, you get temperatures that are significantly higher than those which were observed. So I switched one of my graphs looking back 20 million years ago from a linear fit, which is a slightly better fit, back to logarithm because it just didn't fit the data when CO2 levels get really high. So, that's what I did, and it made sense to me.
The dot points we were seeing weren't the dot points you actually used to fit the curve to.
Oh, yes, they are.
Well, it doesn't look like.
Well, they weren't the only
thing. To some of those early curves.
So I had auxiliary points beyond the range of that data that I was not using more than 50 million, well, actually more than 20 million years ago. And those did not fit well when I used a linear fit. And I really wanted to keep it not inconsistent with as much of the data as I could handle.
Okay.
And I think it's surprised me that when you have the mathematical form you use is very important in the out observations that are larger or smaller, in some way very different from the observations you're using. When you're extrapolating, there's some danger in that, whereas if you're interpolating, there's less danger that you'll get results that don't make so much sense. So those are my thoughts. Okay. But the linear fit was actually a little bit better within the data points, but not outside them.
Thanks, Dev. Robert, Chris?
Yeah, hi. Gene, essentially, the message I get from your presentation is that we've got two things going on here simultaneously. We've got to reduce the warming by decreasing the stock of greenhouse gases. Yep. And simultaneously, we've got to increase the extent to which temperature is being suppressed by ramping up the solar radiation management by whatever technology.
Yes,
So I
exactly.
wonder whether you formed a view as to whether or not we could ramp up the SRM fast enough to offset the incremental warming from the reduction in greenhouse gases, of the stock of greenhouse gases, because of course that is quite slow. I mean, there's 1,100 gigatons of carbon dioxide, of anthropogenic carbon dioxide still resident in the atmosphere. So
Well,
that's what's causing the warming. And
well, at the margin, very much so. But there's only so much we can do with SRM, and you continue to allow CO2 to build up, and you're still up shit creek. You're just up shit creek later. And the best idea is not to be
so
up
much
shit
you can do
creek.
with SRM. I mean, there are
And,
those.
one of the things happen with a good SRM program is the oceans continue getting more acidic, and that has implications, bad implications for life in the ocean, especially calciferous life. And there are many considerations, and that's certainly among them. SRM is much cheaper, and its lead time is shorter than very serious big programs of reducing greenhouse gases. God knows it's cheap to stop putting in the air, but that's starting to happen, thanks mostly to China and their cutthroat competition, bringing renewables prices down.
So are you kind of comfortable that if the political will was there, we could ramp up SRM fast enough to offset the atmospheric greenhouse gases, to bring temperatures down quickly enough to safe levels, back to around 1 degree of warming? I mean, do you think that's feasible?
I think that's probably true. I certainly wouldn't want to stop doing CO2 removal, but I think at this point we're still not so hot. It's about 1.4, 1.5, and we're probably going to pass 2 shortly after 2040, maybe, perhaps, possibly even before then, if we get some more acceleration. And if you can get 1.5 out of stratospheric aerosol injection and 0.6 among marine cloud brightening and nanobubbles on the surface of the water and mirrors in space, mirrors on land, other kinds of things, you can get it down to a safe level, temperatures to a safe level fairly quickly, but you cannot keep them there if you're continuing to have this large load and growing load of greenhouse gases in the air. When we get the temperature down, that slows down carbon sinks, turning to carbon sources, whether it's in the ocean or in forests, where I think we're in a kind of a bad shape. It's interesting, not apropos of your question, but we're seeing this temperature increase accelerating fairly much on land, yet the ocean heat content is, if there's any acceleration in the last 20 years, there's been maybe a little bit. It's up from 10 to 11 zetajoules per year. But that's kind of lost in the noise. You can't say that that's different, that there's definitely acceleration there. There appears to be, but we need more data. That's not a very large acceleration, and it could be due to other things and cycles and so forth. But sorry to
I
not
think we've
answer
just
the
got the
question
time
that comment.
from Bruce.
How about Bruce?
And I had a quick question on albedo. I noticed that you have a formula says here's the relationship between CO2 ppm and temperature, and you get all this albedo at the same time. And I was been puzzling that, what's been the effect of the temperature of the albedo change, and is it possible that albedo is simply a function of temperature increase? Much like the warmer the Earth gets, the more water vapors in the ocean, in the atmosphere, and the more the albedo changes. And you really can't, if
I
you want to
think
change the albedo, you simply lower the temperature.
I think that's true to a very large extent. I hadn't thought of lowering the temperature as rebrightening the Earth, but when it gets cooler, based on what I found about the clouds from Seleucus' work and my redoing of what he did, is that when it's cooler, there are more clouds, as a very general statement. And in terms of it cools off, your sea ice is not going to melt so much, or maybe at all. Maybe it will even regrow. And certainly we've had people working on that. So I think
it's probably hysteresis loop. It'll eventually get back.
Yeah. So yeah, we cool things off and we can increase Earth's albedo. We'll get more snow, we'll get more ice, and we'll probably get more cloud cover. And those are the big ones I think of.
Great. All right. Well, thank you very much, Gene, for an excellent presentation, and we look forward to sharing it on the Healthy Planet Action Coalition website. And it's really given us some really important food for thought. So
I'd like to add something.
If you could just make a final comment, please.
I hope to update the projections within the next year. It's a few hundred hours, and to have stuff for albedo effect and one for CDR and one for them combined. And I think that will tell a good story to the public.
And will you share your slide deck with HBAC?
Oh, yeah. Oh, yeah.
Great. Well, we look forward to putting that
probably up. Probably post this to my website maybe tomorrow or the day after if I figure out how to do that.
And what's your website?
www.globalwarming-sowhat.com.
All right. Well, there we are. We've hit the top of the hour. So thank you all very much for coming along. And we look forward to continuing the conversations. Thank you.
Thank you, Gene.
Bye all.
Great.
Thank you, everybody who joined us.